Okay, so now that you've looked at a few sections, you know how integration works, you know how definite integrals work, and you looked at the sums, Riemann sums. It's time to look at one of the very important techniques for integrations. It's called U-substitutions. And U-substitutions are used primarily when we're trying to evaluate integrals of composite functions. So suppose we had to integrate something like the integral of f of g of x times g prime of x dx. So the first thing you probably recognize is that you have a function g of x inside of f here, so that's a composite function. And then on the outside, you have the differential of g of x. So this is the differential of g of x. And so we might see if there's some sort of substitution. And just as we might have done in algebra, we're going to let u replace our function g of x. So if we let this be u, and of course u is a function of x, then this over here is du with respect to x dx. And so if we look at our Leibniz notation, we get some cancellations there, and this integral becomes the integral of f of u du. So something pretty important happens when we have something that has a structure of f of g of x times g prime of x dx, and that is we can make a substitution, and then from that substitution we can get a simplified integral. So let's kind of codify that on this next slide. So if I have the integral of f of g of x times g prime of x dx. Now, of course, that has to be a special structure, right? Then we let u be equal to g of x. When we take the differential du, and we get du as g prime of x dx. And then we simply substitute those pieces back into the integral above. So that will go there. And this part, of course, is here. So my integral becomes the integral of f of u du. Okay, so let's look at some examples. So suppose I had the integral of x squared plus x plus 1 times 2x plus 1 dx. So if I look at that, I have a trinomial times a binomial. I could multiply that out. If I do, I get a long polynomial, and hopefully I didn't make any mistakes, and then I have to integrate each of the pieces. Or I could take a look at it here and let this be u, so x squared plus x plus 1 is u. If that's the case, what's the derivative of u? Well, the derivative of u would be 2x, because the derivative of x squared is 2x, plus 1. So it turns out that if I let u be equal to x squared plus x plus 1, du is exactly 2x plus 1 dx. So I have a perfect substitution. This becomes the integral of u du. And when I integrate u, I get u squared over 2 plus a constant from my power rule. And of course u was equal to, flip back there, x squared plus x plus 1. So the antiderivative is x squared plus x plus 1 squared over 2 plus a constant. There I have my solution. Okay, let's look at another example. So suppose I had something like the integral of 2x e to the x squared dx. Again, I'm hoping that I see something that looks or resembles the integral of f of g of x times g prime of x dx. So I look here and I notice that I have an x squared here and I have its derivative here. And so this integral starts to look more like the integral of e to the u du. If I just go to the next slide, I have the integral of 2x e to the x squared. Get that out of the top there. E to the x squared dx. If I let u be equal to x squared, then du is equal to 2x dx, which is exactly the portion that is left over here. There's a 2x and the dx. Substituting directly in, everywhere I see an x squared, I put a u, and everywhere I see a 2x dx, I replace that with du. So my integral does become e to the u du, and the antiderivative of e to the u is e to the u plus a constant, and I see that u is x squared, so this integral is equal to e to the x squared plus a constant.